Hi all. In this presentation, me and my team are going to discuss about optimization approaches for path planning and unmanned aerial vehicles UAVs. Imagine we have a drone and we need to get it from point A, the starting position, to point B, goal position. Now in this path, we of course are going to have some obstacles and we don't want the UAV to hit them or die out midway and make sure it reaches the destination properly. Also, it should fulfill some objectives like path optimization. It should select most efficient route from the starting point to the goal, minimizing the distance and ensuring smooth transitions. Time efficiency, it should minimize the total time taken to reach the destination. Collision avoidance, navigate around obstacles and avoid collisions with static and dynamic objects in the environment. Cost efficiency, reduce the overall cost of the journey, maximizing the profitability and reduce the resource wastage. So this is JV path planning all about, fulfilling the objectives and satisfying the constraints. Now, to make these goals a reality, experts came up with super clever techniques. Over time, these methods have seen continuous improvements, making them more effective and efficient. In this presentation, we are going to explore these different approaches and see how they evolved to tackle the challenges of the path planning. Classical path planning approaches, the ancient ones. These are the approaches which provide structured, minded deterministic methods for UAV navigation using well-established algorithms. Why use classical applications? It guarantees optimality in static environments, that is, a setting where the obstacles and the layout do not change over time. These uses graph-based and geometric algorithms. Graph-based algorithms like A star and Dijkstra represent the environment as a graph, where nodes represent the possible positions and edges represent the possible paths. Geometric algorithms such as RRT, rapidly exploring random trees, use the geometry of the environment to find paths by considering the shape and position of the obstacle, effective for map-based pathfinding. This map can be a grid, a graph, or a continuous space, and it provides information about the layout of the terrain. Now, this is a quick comparison of all the classical approaches. Before this, I'm going to explain each approach in short. RRT. RRT is rapidly and exploring random trees. It is a sampling-based method used for pathfinding in high-dimensional spaces. Sampling-based methods utilize random samples to make decisions, estimate values, or solve problems. They are often employed when it's unfeasible to analyze an entire dataset or problem space exhaustively. It builds a tree by randomly sampling points in environment and connecting them to the nearest node in the tree, expanding towards the goal. It repeatedly randomly picks a direction, walks a few steps, and marks the spot with a flag, slowly building a path. If it sees an obstacle, it stops and tries a different path. Next is Voronoi diagram. As it can be seen in this diagram, Voronoi diagram partitions a space into regions based on the distance to a set of points. In the pathfinding, it helps by generating paths that maximize the distance from the obstacle. It wants to avoid the obstacle, so it works on paths that keep it as far as possible from every obstacle. Artificial potential field. It uses attractive and repulsive forces to guide a robot. The goal generates an attractive force, while obstacles create repulsive force, combining to provide a gradient that directs the motion. This is very intuitive as we want to go towards the goal and avoid the obstacle. Visibility graph. A visibility graph connects all the vertices of obstacle and the start goal points if they have direct line of sight. The shortest path is found using graph search algorithm. As it can be seen in the graph, we are considering the geometric dimension of the obstacles to find the path. Now, the Dijkstra algorithm, it finds the shortest path in weighted graph by exploring all possible routes and selecting the path with the minimum cumulative cost. The PRM, probabilistic roadmap, as it can be seen in this diagram, it is another sampling based method that creates a roadmap of randomly sampled points, connecting them if the direct path is collision free. It's like an algorithm, it is in the dark space and is randomly shining its flashlight in different direction and it marks the safe spots to walk to. Now, we can clearly see in this table the strengths and weakness of all these algorithms. RRT, it works in high dimensional spaces, it ensures completeness, but it requires path smoothing, high computation in complex environments. Voronoi diagrams, it provides safe paths, works in real time, but path length is not optimal. It struggles with complex obstacles. Artificial potential field, it is simple, fast and ensures collision avoidance, but local minima problem, inefficient in dense environments are common problems in this algorithm. Visibility graph, shortest path for polygonal obstacles, but it is computationally expensive for complex graph. Dijkstra algorithm guarantees shortest path optimal for static maps, but it is again computationally expensive. It cannot handle dynamic obstacles. The probabilistic roadmap is efficient for multi-query path planning, but it requires pre-processing struggles with dynamic changes.
These classical approaches are foundational and they have some limitations. That's why heuristic came into the scenario. So, heuristic path planning for UAVs. Heuristic methods provide fast, near optimal solutions for UAV path planning by using intelligent search strategies. They trade global optimality for computational efficiency. Now, let's talk about why heuristic over classical through these points. Our first point is computational efficiency. Like classical approaches search a large portion of the search space, leading high computational cost, where a heuristic approach guides the search more intelligently, reducing unnecessary computations and speeding up the convergence. Second, scalability. While classical suffers from exponential growth in computation as the number of obstacles and waypoint increases, heuristic uses domain-specific knowledge to find the near optimal solution. Our third point is handling dynamic and uncertain environments. Uh, what I see in real time, there are many real time obstacles we have, like wind disturbance, changing the mission objectives. There may be some weather conditions are included also. So classical approaches struggle to adapt in real time, where heuristic methods can quickly adjust to such kind of conditions. Our last point is multi-objective optimization, where UV path planning requires balancing multiple constants such as minimizing the energy consumption, avoiding obstacles, reducing the time travel. Also, we have to avoid the no flying zone. Classical methods generally optimize for a single objective, whereas heuristic allows for flexible trade-off. Let's talk about some common heuristic in UAV path planning. First, Euclidean distance heuristic measures the straight line distance between the UAV and the goal. This Euclidean distance heuristic is used in open space where the UAV can move in any angle. So basically the smooth movement is possible while using this Euclidean distance heuristic. It is used in A star algorithm and theta star algorithm. Secondly, Manhattan distance heuristic computes path length based on grid-based movement, only horizontal and vertical steps allowed. So as we say, only horizontal and vertical steps are allowed. So basically we are restricting the movement of the UAVs. It is used in grid-based A-star algorithm. Thirdly, hybrid Euclidean heuristic function. It combines Euclidean distance with other factors such as wind speed, no flying zone, and we use it in multi-objective UAV path planning. Now let's talk about some algorithm used in heuristic. The first algorithm we are going to talk is A-star algorithm. So, A-star is widely used heuristic search algorithm for UAV path planning due to its efficiency, optimality, and flexibility. It uses the concept of two algorithms. First is Dijkstra algorithm, and the second is greedy best first search algorithm. Dijkstra algorithm helps for shortest path, and the concept of greedy best search, best first search use for fast exploration using heuristic. The weakness in A-star algorithm is its struggle with dynamic obstacle. The second algorithm is bi-level programming. Bi-level programming is a hierarchical optimization framework where one optimization problem depends on the solution of the another. It balances mission level objective with real-time navigation constraint. As for example, while planning the UAV path, minimizing travel time is our mission level objective, and avoiding no-fly zone is our real-time navigation constraint. So the weakness is high computation for multi-UAV scenario. The third algorithm we are going to talk is LKH. It is cost efficient and smooth path. It is basically used for large scale TSP problem where we get near optimal solution, but it has high computational cost. The fourth algorithm is theta star algorithm. It is non-grid based navigation algorithm. So the smooth movement of the UVs are possible here, but it struggle in dynamic settings. In greedy algorithms, it is simplest, fast, energy efficient, but does not guarantee optimality.
Interestingly, researchers also peeked into the nature and inspired from it, which led to meta-heuristic approaches that are high-level optimization techniques that mimic natural processes to find near optimal solutions to complex problems. These methods are particularly useful in large, dynamic, and high-dimensional search spaces, where traditional methods struggle due to their deterministic nature and tendency to get stuck in local optima, as meta-heuristic approaches focuses on exploration for global search and exploitation for local search. The key characteristics of meta-heuristic approaches are these are nature-inspired algorithms. These are inspired from biological, physical, or social processes. These introduces randomness and probabilistic search. Unlike deterministic heuristics, meta-heuristic use controlled randomness to explore new solutions. These uses exploration and exploitation in balance. These are adaptable to complex problem spaces. How meta-heuristic algorithms works these are in such a way. Firstly, initialization takes place in which n number of candidate solutions are created. Then evaluation in which the best of the candidate solutions are taken out using some optimization function. Then using exploration and evaluation, we find further best solution from our candidate solution which is chosen. In convergence check, we check if the solution which is taken out is the optimal solution or not. First of the algorithm of meta-heuristic approaches is genetic algorithm. These are inspired from human evaluation. In this, chromosome represent the solution and gene contained by chromosome represent solution parameter. How this algorithm works is firstly we initialize some n number of chromosomes. Then selection of two of the best solutions from the population takes place based on the objective function which gives fitness score. Then crossover takes place in which it generates offspring by combining parts of chromosomes. Then mutation takes place in which small changes in offspring is done with some low probability. From available chromosomes and offsprings, best solution is taken out and these same steps takes place further in further iterations. Then particle swarm optimization. This algorithm is inspired from bird flocking. It is based on the social behavior of bird flocks and fish schools. It optimizes a solution by having a swarm of particles move through a search space, adjusting their positions based on personal best and global best solutions. PSO efficiently balances exploration and exploitation, making it ideal for UAV path planning. Then comes the ant colony optimization. These are inspired from ant foraging, in which they search for food. Similar to how ants spread pheromones on the path they use to go from nest to food, similarly we assign some numerical pheromone value to each path taken to reach the goal node. In each iteration, in next iterations, the UAV will
Either choose the path with highest pheromone value or will explore some new path based on exploration and exploitation parameter. The old pheromone value decreases with time or iteration. It will continue in further iteration either till it finds the best solution or the maximum number of iterations take place. In the end, the path with highest pheromone value will be the best path as per ACO algorithm. Then the last algorithm will be Gray-wolf optimization. It is inspired from wolf hunting. It is based on the hunting behavior of gray wolves. It uses hierarchical leadership structure in which alpha, beta, delta, and omega wolves define the hierarchy of the wolves to balance exploration and exploitation, making it effective for UAV path planning optimization and multi-objective problems. The few of the limitations of meta-heuristic approaches are these are these carry high computational cost. These do require some parameter tuning for optimal performance.
Instead of searching through solutions or building the solution as we have done till now, ML approaches learn from data or experience to find underlying optimized path. The increase in generalization and ability to handle high dimensional data is key point to use ML approaches. Due to complexity and dynamic nature of environment, it is not possible to directly learn the path. Supervised machine learning methods generally focus on single objective such as collision avoidance and restricted area detection. RBF is an supervised ML algorithm which cleverly learns to avoid obstacles using radial basis function. Activation of RBF exponentially increases with decrease in distance from the node point. It is good at obstacle detection due to simple but effective activation. There are such methods such as PDE, Gaussian process, which are able to handle multi-objective planning, but they are computationally expensive. So the other class of machine learning approaches which tackles above problems is reinforcement learning. RL models learn with experience and consist of an agent reacting to the environment. Action taken by agent changes the configurations of environment and reward is given to the agent based on how good the action was. The agent learns to take unit actions repeatedly to trace the optimal path. It is like teaching a child how to ride bicycle. The child will fail multiple times, but based on the experience, he or she will learn the goodness of an action at the point of time. Design of good reward function inculcates multiple objectives in the model. Cumulative reward optimization helps for global multi-objective optimization. DQN, D3QN, Deep Sarsa are some RL models. They are proved to outperform many other approaches in dynamic environment. Reinforcement learning methods are better for dynamic environments as it takes decision for every unit action repeatedly based on observed environment at the point of time. A method worth mention is cooperative and geometric learning. Cooperation among multiple UAVs is implemented by real-time information sharing between UAVs. It helps to work better in complex environments which are highly dynamic. And geometric data provides good sense of spatial information. It is due to these kind of cooperative methods you are able to see eye-pleasing drone shows. The challenges for ML-based path planning algorithms still resides. High computational cost makes real-time deployment tricky and training these models require massive label dataset. So to bring out best of multiple worlds, hybrid approaches are also being developed. It is used to leverage their individual strengths while mitigating their weaknesses. The goal is to efficiently compute an optimal path that satisfies multiple objectives. The paper talks about 5 types of hybrid approaches: classical with heuristic, classical with meta-heuristic, meta-heuristic with meta-heuristic, and meta-heuristic with machine learning. Traditional algorithms like A star guarantee optimality but struggle with real-time adaptability. Particle swarm optimization efficiently explore a large search space but can be slow. Machine learning and reinforcement learning can generalize from experience and adapt dynamically but require extensive training data. A hybrid approach integrates these techniques to enhance UAV navigation in dynamic, uncertain, and complex environments. For example, A star with genetic algorithm. A star is used to generate an initial path quickly, then genetic algorithm refines the path to optimize objectives such as energy efficiency and smoothness. This reduces the search space for genetic algorithm, improving conversion speed. Hybrid approaches provide a robust, adaptive, and efficient way to solve UAV path planning by integrating the strengths of different algorithms, whether combining search, optimization, ML, or RL. These approaches enable UAVs to navigate complex, dynamic environments while satisfying real-world constraints. Even after giving multiple powers to a method, hybrid approaches have limitations of higher computational cost and complex parameter tuning. For example, A star search is fast, but when combined with particle swarm optimization for refining the path, the total computation time increases significantly. So, after studying too many path planning approaches, we can say no single model is a best all-rounder. Traditional path planning methods like classical and heuristic approaches are fast but struggle with adaptability. Meta-heuristic methods enhance global search but come at high computational cost. Machine learning and reinforcement learning introduce self-learning capabilities, making UAVs more autonomous, but they demand large dataset for training. The best solution in terms of cost optimization and collision avoidance, it can be hybrid approaches. They strike a balance between accuracy, speed, and adaptability, making them ideal for real-time UAV navigation. In the fast evolving world of UAV path planning, no single approach is perfect for every application. Minded for every application. But by combining speed, intelligence, and adaptability, we can create smarter, safer, and more efficient UAVs. The autonomous navigation isn't just about finding the best path, it's about learning and adapting. This was our presentation on UAV path planning approaches. Thank you for your attention.